Good. Hello, everyone. Thank you for joining my presentation today. My name is Wuchal Remy, and I'll be discussing graph theory, graph algorithms, theory, implementations, and applications. This presentation will provide a comprehensive overview of essential graph algorithms, their theoretical foundations, practical implementations, and real-world application. Graphs are fundamental structures in computer science representing a wide range of real-world problems, from networking to social media and bioinformatics. Graph algorithms play a crucial role in solving complex issues efficiently. In this presentation, we'll explore several key graph algorithms, including breadth-first search, depth-first search, and MSTs and shortest path algorithms as well, and discuss their importance and applications. Let's start with the basics. A graph is a collection of vertices or nodes connected by edges. Graphs can be directed where edges have a direction or undirected where edges have no directions. They can also be weighted where edges have weight or cost or unweighted. Understanding these fundamental concepts is essential for working with graph algorithms. Breadth-first search, or BFS, is a traversal algorithm that explores all neighbor nodes at the current depth level before moving on to the next level. It is particularly useful for finding the shortest path in unweighted graphs. The algorithm involves initializing a queue, marking the starting node as visited, and then dequeuing nodes to explore their unvisited neighbors. Breadth-first search is widely used in social network analysis and level order traversal of trees. Depth-first search, or DFS, explores as far as possible along each branch before backtracking. It's useful for tasks such as detecting cycles, performing topological sorting, and finding connected components. Depth-first search involves initializing a stack, marking the starting node as visited, and then popping nodes to explore their unvisited neighbors. It's commonly used in applications such as maze solving and web crawling. A minimum spanning tree MST connects all vertices in a graph with the minimum's total edge weight. Two primary algorithms for finding MSTs are Kruskal's and Prim's algorithms. Kruskal's algorithm sorts edges and adds the smallest edge weight, avoiding cycles, while Prim's algorithm uses priority queue to add the smallest edge connecting to the MST. MST algorithms are crucial in network design and clustering. Finding the shortest path in a graph is a common problem. Dijkstra's algorithm is ideal for graphs with non-negative weights, using a priority queue to repeatedly extract the node with the smallest distance. The Bellman-Ford algorithm, on the other hand, handles graphs with negative weight cycles and detects negative weight cycles. These algorithms are essential in routing and logistics applications. Understanding time and space complexity of graph algorithms is crucial for evaluating their efficiency and scalability. You can see here there's a graph that represents their time complexity and space complexity. Of course, it's important to match the time complexity with what is relevant for what we're trying to use for the use case. Graph algorithms have numerous real-world applications in network routing and optimization. Breadth-first search and depth-first search are used for traversing networks, while Dijkstra's and MST algorithms optimize routing and minimize costs. For example, internet browsers use the shortest path algorithms to determine the most efficient path for data packets, and MST algorithms help design cost-effective road networks. In social network analysis, graph represents individuals and their relationships. Breadth-first search and depth-first search help in community detection and influence maximization. Social media platforms like Facebook and LinkedIn use graph algorithms to recommend friends and analyze user connections. In AI applications, graph algorithms are used for pathfinding in games and robotics and recommendation systems, leveraging graph algorithms to identify relationships between users and items. Graph theory has a rich history, starting with Euler's work on the seven bridges of Königsberg's problem in 1736. This laid the foundation for graph theory. In the 20th century, Dijkstra introduced his shortest path algorithms, and Kruskal and Prim developed their MST algorithms. Modern advancements included graph neural networks and quantum computing, which promise to solve graph problems more efficiently. Graph isomorphism involves determining whether two graphs are structurally identical. Network flow algorithms like the Ford-Fulkerson method find the maximum flow in a flow network. Spectral graph theory studies the properties of graphs using the eigenvalues and eigenvectors of matrices associated with the graph, with applications in clustering and image segmentation. Implementing graph algorithms requires addressing challenges such as disconnected graphs and cycles. Efficient memory usage and runtime performance are critical. For example, Google Maps uses shorted path algorithms with real-time traffic data to optimize routes. Facebook's Friends recommendation system uses BFS and DFS to explore social graph, and genomic research graph algorithms help identify critical genes and pathways involved in genetic disorders.